Hey guys, it's February 18th. Excuse me, it is not. It is February 8th. Super Bowl Sunday. Super Bowl Sunday, and I want to go through. I'm kicking off a new deck appropriately. A new slide deck, Google Slide Deck. I'll have a link. As usual with my decks, as you know, I encourage you to share them if you're a teacher or you just want to have something to share. You can say, "Hey, look at this deck I found. Cascadian Synergetics. What's that? It's curiosity." You could come at it from that point of view. Show and tell. Show and tell. So we have these animated GIFs, and I wanted to talk a little bit about each of the 17 slides here and give you a sense of what's in this deck. Although, if you've been taking my course, which is called School of Tomorrow, Winter Term is what's going on now. It's all asynchronous, not all, but pretty much people just read around, explore, and it's like it jumps out of my website a lot. It's like it's not me keeping you a prisoner here, and I'm expecting that you're going to look at the original text online or in hard copy of synergetic geometry, which is what's being talked about here. That green cube is our famous volume 3 cube, inside of which are inscribed as face diagonals two alternative unit volume tetrahedra, orange and black in this color scheme, creating the volume 3 cube, which is, you could say, their intersection creates this union of this cube. I mean, it's really just two duals begetting another shape, the cube. And the cube has a dual. By dual, we mean faces become vertices, vertices become faces. The edges, we make them crisscross. The idea of a dual, it doesn't really specify the relative size of the two shapes, but if we make the edges crisscross, then we beget yet another shape, the blue. You can see how the green and the red come together, right? Just as the black and the orange come together to make the green. So the green and the red come together to make the blue. The blue is the rhombic dodecahedron. And it has volume 6 in our concentric hierarchy, meaning they share a common center, and the red octahedron has a volume 4. Now you'll notice the individual edges are also colored in a certain way, and that has to do with the color coding system that we are not going to get into in this particular walkthrough of the slides. Now, well, we almost do actually, because on the right side I continue with that color scheme. Let me just say there's a 4-frequency tetrahedron made of clay balls, meaning that there's 4 intervals along each edge between 5 balls, right? There's 5 balls along the base, but then the next layer up, 4 balls along each edge, and at the center there's this orange ball that's equidistant from all the face centers and all the vertices of the surrounding tetrahedron once we put the top back on. By that I mean over to the right you see, starting with a 2-frequency or 3-ball layer, and then smaller and smaller up to an apex ball that's red. If we put that back on to the base, then you can see how the orange ball is equidistant from the red ball, the yellow ball. In the shadows there it may be a little hard to tell, but the ball there on the far right of the base is the yellow ball, and then there's a blue ball towards us, a green ball. And once you've got this whole thing assembled, you can tilt it in various ways. Like you can have the green ball be the apex ball if you want, and there are other discussions where that's what we do. The left is basically a recap of what I was describing earlier. On to the next sequence, or animated GIF. This one we get into the 5-fold symmetricals. In other words, rhombic trichondihedron, icosahedron, pentagonal dodecahedron. But we're doing the same sort of process of intersecting duals of one another. And we're sticking with platonics, you could say that too. In other words, in the previous slide, let me just go back to that. These first two, the tetrahedra, orange and black, those are platonics, duals of each other. We usually talk about the platonic five, but if we agree that the two tetrahedra are each to be counted separately, then we would have platonic six, and then the cube and octahedron form a pair, and then also the platonics, where we were just looking, the icosahedron and pentagonal dodecahedron form a pair of duals. That's the relationship between the two, and they beget, just as the octahedron and cube beget a rhombic dodecahedron, so do the icosahedron and pentagonal dodecahedron beget the rhombic triconahedron, which shows up in purple. It's very clear that the first two, the cyan and the brown, crisscross each other and beget the purple RT, but then it shrinks to embrace the ball. It shrinks down. Actually multiply all the edges by 1 over phi in order to shrink it down. And that ball it's important to us. It could have appeared in the first image as well. I don't have the ball in this version. Oh, I do. There's the ball. Excuse me. Same ball, same size. I'm glad I do have it. I was thinking that would be something to add, but there it is already. So there's the ball again. Same ball. We say it has diameter D and radius R, and that lets us talk about other lengths in those terms. Like in the first picture, all those orange and black edges are length D, as are the long diagonals, the red edges of the rhombic dodecahedron. Now in this picture, the cyan icosa has edges D, and then the pentagonal dodeca has whatever edges it needs to make that dual, and then we have this shrink down of the RT to sphere embracing. Now that's a lesson. That's a lesson in itself, but then we can go deeper if we like and talk about different sizes of rhombic triconahedron relative to each other. There's the icosahedron, as we also discussed, and the pentagonal dodecahedron. And here you see algebraic expressions, which could be simplified if we allowed ourselves to use the phi symbol to stand in for some of this, you could call it extraneous clutter. Like, I know how I could simplify these as an exercise. If you're a teacher and you're getting into algebra and substitution, and whoa, we have the symbol 5 for square root of 5 plus 1 over 2, all over 2. Well, I see that. I could put that in. The icosahedron could be 5 times the square root of 2 times phi to the second power, for example. However, that's in tetravolumes. Again, this is synergetic, so it's all, when we say volume, we mean relative to the unit volume tetrahedra as shown in this slide. So this is just a screenshot. These links don't actually go anywhere, but this would be, I think I'll add in the comments a link to the Jupyter Notebook where this all comes from for more context. Because with these slideshows, you're not just going to have to stick with the slides. If you have other things in other tabs that are open, we're in a browser after all, you can jump out of the slides and jump to what I call auxiliary exhibits. Okay, we're like about a third of the way through. This is another lesson plan, you could say. We're going to just start with the isosceles triangle as a concept, right? Two sides, same length, there's an included angle, and what we're curious about is how to find that third side, the one opposite the included angle, right? You see those tick marks, same side, same size, same length size, sides, same length sides, same size sides, you could say S. We get a formula below, how to get the base based on the length S and the cosine of the angle, included angle. Now, this implies that we're into trig already. It's like, what level of student are we talking about here? How much trig do they know? Well, here I'm including, after asking Google in a very friendly way, to share a derivation of said formula, this one at the bottom for the base. Where'd that come from? I asked. And Google comes back with a step-by-step derivation beginning with the law of cosines. So what I'm thinking is this is a high school level, you could say, but that doesn't mean you can't teach it at a different level, like at community college level or whatever. Trig always comes back, and you can always go through these slides faster if you're on a higher level in the spiral. And you can say left for homework or confirm this for yourselves or whatever, assuming the students can go back and look at these slides later. And then I turn immediately to two isosceles triangles that are going to be of interest to me. One of them is, I call it the vein. And where is this triangle? Where does it appear? Well, think of a regular tetrahedron, which I kind of allude to on the left here with the caltrop. What we're looking at is the center point of a regular tetrahedron and the four branching spokes coming out from that center to the four corners of the tetrahedron, which isn't actually drawn there. We just see the spokes. I'll call them Q0, Q1, Q2, and Q3 here, or letter them A, B, C, D. Those are the four spokes. How long are those spokes? If the edges of the enclosing tetrahedron are all D. And let's set a number for D. Let's say D equals 1. Now, on the right side, I'm actually getting into the angle of 109.47 approximately degrees that will be in that regular tetrahedron, and the spokes will all be second root of 6 over 4. You also have that length from the center of the tetrahedron to any mid-edge of the tetrahedron. That's going to be second root of 2 over 4. And then the edge itself of the vein of the tetrahedron and of the face diagonal of the cube. So we're back to our opening cube here, the green cube. Notice its face diagonals are all orange or crisscrossing the other way, all black. That's our edge D, that's our length 1, and therefore you see the two 1/2s. Considering the right triangles that are being made here using Pythagoras to confirm that these edges all fit. And then this is another picture of the vein, believe it or not. This is thinking more like looking down from a drone point of view on a desert highway that just goes straight. But as there's this turnoff at, what is it, roughly 35 degrees, whatever's left over, 180 minus the 109.47, split that in half, and that's what the other two angles will be. But we're looking at a gas station. Looking down, there's a stretch of road a mile long. We leave it at this angle and go for 0.61237 miles, square root of 6 over 4, second root of 6 over 4. Then we turn 109.5 or 47 degrees after tanking up, filling up with gas, and we go back to the highway. And this time we go exactly the same distance, 0.61237 miles, second root of 6 over 4, and we're back at the highway. That's another way to think about this vein. It's as if the dotted edge of the tetrahedron were the highway, and the turnoff to the gas station was a visit to the center of the tetrahedron as kind of a side trip. There's like a gas station at the center of the tetrahedron, we could say, in this particular picture. And then this is the other isosceles triangle I want to talk about. And you can see that the relationship I'm interested in, all the edges of this regular pentagonal shape, the pentagon, are 1. But the diagonals, there are 2 of them shown. You can make a star with more of them if they could intersect. You can draw it. These are simulating actual plastic rods with magnets on the end, steel balls. This was a toy called Strange Attractors. It's a rendering of that. So that's why there's all these details and cone-shaped. There's actually magnets at the end of those cones to click onto the ball bearings. But those longer purple diagonals, those are phi. Some people say phi, I say phi, but you know the number 1.618 dot dot dot. So longer than the edges. You can see purple is longer than red. And then we've got all these trigonometric relationships. So again, between the two of these lesson plans, we've got a lot of trig, and that's the whole point. That's what I wanted to get into. But also we're coming from, you could say, a volumetric approach to geometry. And this is signature how we do things. We're interested in real world sculpture, kind of all-dimensional volumes. And then we can get various planar shapes extracted from that. Like we do get to planar geometry, but it's really normal and natural to start with like everyday objects like furniture or cars. In other words, real life is not planar. We don't start from the chalkboard and build up. We go to the chalkboard from volume. We start with volume, concentric hierarchy, and pouring water from shape to shape, getting relative volumes, linear dimensions from there. And this is our last lesson plan. This is from the web page. I'm going to find this web page and give credit to it in the teacher's notes here. Again, this slide deck, I just threw it together last night, so it's not complete. I'll be adding to it. And this is showing a conventional textbooky approach to figuring out the density of the CCP, or close cubic packing, also known as the FCC, or face-centered cubic. You can see where it says in the lower right box for FCC. And they figure out a cube that has enough of each ball in the CCP. It's a way of packing balls together. Get the minimum cube that if you were to tile space with this cube with the balls in it, fractional balls, it would end up making the CCP. So we only have eighths of the ball in the corner and then half balls coming in, protruding into 6 faces of the cube. So we've got the cube edge of A. We got to figure out how much volume is taken up by the yellow spherical parts and do a division. Spherical parts divided by total cube volume equals percent full, or percent density. How much of space is occupied by the CCP vis-a-vis empty space? And their computation boils down in lower right to 74% after we simplify the algebra. And this shows doing that on a Google calculator. Same computation, lower right-hand corner, pi over 3 second root of 2, pi over 3 second root of 2, about 0.74, or 74%. Now, in the synergetics world, that magenta cube there, that's going to be our R-edged cube. Remember, R means radius of one of these balls. The balls will be packed in the same CCP conventionally. In synergetics, that's kind of the context. The balls are in a CCP lattice. Around each ball, we have these polyhedra oriented in a certain way, certain relative size, nested polyhedrons. The magenta cube would be our traditional cube, the one we're used to from XYZ, from Euclidean geometry, that we always say is unit volume. And its edges are R, or unit. And yet, here in this system, we're going to say it's irrationally volumed, 1.06066. And it's the green volume, which has diagonals D, 2R. That's the one that we're going to call volume 3, vis-a-vis our tetrahedra, which are going to be volume 1. It's like that magenta cube's volume vis-a-vis our tetrahedron is a little bit more, 1.06066, like 6% more. So this is back to that very first slide and that very first animation. They're in the same orientation, same size. This is our 1, 3, 4, 6 volume hierarchy. And then we get back to that 1, 3, 4, 6, except we also include the magenta cube of old, ye cube of everyday before synergetics, right? Different way of doing calibration. And there's a reminder of the synergetics constant, how we have to multiply our XYZ volume by what we call S3, 1.06066 square root of 9/8, basically, second root of 9/8. And on the right there, you see the inner cube and the outer cube. That's not supposed to be like a tesseract or anything. This is just ordinary cubes, one smaller than the other. One has edges 1. The bigger one, in terms of R units now, in other words, radius units, if we call the inner cube R edges, then the outer cube has second root of 2 edges, and diagonals would be 2, which in this case would be diameter, twice as much as the radius. So diagonals of the outer cube are twice as long as the edges of the inner cube. This is how S3 is derived. This is where we compute the scale factor needed to go between XYZ units and what we'll call IVM units. IVM is isotropic vector matrix, and it's the same as the CCP, but just looking at the edges connecting ball centers make the balls go away. That sort of scaffolding that's left is the isotropic vector matrix, just like the XYZ scaffolding, in contrast, is all cubes. The IVM is tetrahedra, octahedra, also known as the octet truss. So once we've got this synergetics constant in play, we can multiply the XYZ volume of the ball, which is 4/3 pi r to the third power. If r equals 1, multiply that by second root of 9/8, you get second root of 2 pi as the volume of the unit radius sphere. So that's the new volume that we use, and we ratio that to the volume of the rhombic dodecahedron in which every ball is contained. Those pack together, those RDs, rhombic dodecahedra, they pack together to fill space inside of which each one there's a ball. So the ratio of full space to empty space, again, we could just take the total volume 6 of the RD and divide by the new volume of the sphere, pi second root of 2, and we do that computation in this Google slide. You see us multiplying the conventional volume of the sphere by second root of 9/8, in other words, synergetics constant, dividing by 6, the volume of the RD in our system, and we get the same answer as you would expect, 74%. There's another picture of what the CCP looks like. Those balls, 12 around 1, are each encaged, you could say, in a rhombic dodecahedron of volume 6, and they're all intertangent to the spheres at the diamond face centers. And then the last lesson, of course, we always want to allude to the real size of Greenland relative to the other continents and everything about electrical grids and so on. This is back to Earth, getting back out of metaphysics and into ordinary macroscopic Earth, more like the getting back to more like the geoscope here. This would be yet another jump-off point into our curriculum. So I'll end with that. I'll be adding some speaker notes, of course, and talk again soon.